Good morning, or afternoon, or evening, or night, everyone. This is Professor Positron from Fancy Science University. I'm currently located in my office in the Dutton College of Chemistry with a camera, which should be plainly obvious considering my lecture has been recorded and posted online, but I digress. So I'm here to teach you viewers about solubility equilibria and the solubility product constant, so you'll be more prepared to encounter it on the AP exam. So let's get to it! Okay, in order for an ionic salt to dissociate in a liquid, it must reach equilibrium. Hopefully you have some prior knowledge of chemical equilibrium and equilibrium constants before watching this video. If not, go brush up on that first, and then come back. For example, let's say we put some solid calcium fluoride into water. When it is first added to water, there are no calcium ions or fluoride ions present. When the water molecules pull the ions in the solid apart, the greater ion concentrations make it more likely for the ions to come back together as a solid. Therefore, the forward reaction and reverse reaction reach dynamic equilibrium. An equilibrium expression can be written from this phenomenon. We use Ksp to denote the solubility product constant for the equilibrium expression. In general, if you are given a chemical equation at equilibrium like this, with ion coefficients x and y for ions A and B respectively, then in the Ksp expression the coefficients become the powers. This should not be a surprise to you if you know that in order to write a general equilibrium expression, the coefficients become the powers and solids are left out of the expression. It should be noted that Ksp is not the same as solubility. Solubility is determined using the Ksp expression and solving for a single concentration using algebra like this. I have denoted molar solubility as the variable S. Although full knowledge of solubility rules are not necessarily required anymore on the AP exam, it is important to note that all sodium, potassium, ammonium, and nitrate salts are soluble in water. Let's say you had to compare solubilities of salts. If the salts being compared produce the same amount of ions when dissolved, then the larger Ksp means it is more soluble, and a small Ksp means it is less soluble. Relative solubilities can be predicted by comparing Ksp values only for salts that produce the same total number of ions. So, if the salts being compared produce different amounts of ions when dissolved, calculate the solubilities of each using algebra. There are some factors that affect the solubility of a salt. Temperature is a given because it affects all equilibrium constants. If one of the ions in a solution equilibrium is already dissolved in the solution, the equilibrium will shift to the left to undo the stress on the right, and the solubility of the salt will decrease. If you're familiar with Le Chatelier's principle, this should make perfect sense to you. This phenomenon is known as the common ion effect. The pH of a solution can also affect solubility. If a substance has a basic anion, it will be more soluble in an acidic solution, since adding a basic substance to a basic solution will cause the equilibrium to shift to the left to undo the stress on the right. If a substance has an acidic cation, it will be more soluble in a basic solution, since adding an acidic substance to an acidic solution will cause the equilibrium to shift to the left to undo the stress on the right. You can use Ksp and the reaction quotient Q to determine if a precipitate will be formed in the reaction. If Q equals Ksp, the system is at equilibrium and the solution is saturated. If Q is less than Ksp, no precipitation occurs, and increasing the concentration of the solute will make the system reach equilibrium. If Q is greater than Ksp, a precipitate is formed, and decreasing the concentration of the solute will make the system reach equilibrium. One final thing about solubility is that delta G can be used to determine the thermodynamic favorability of the dissociation. If you're not familiar with Gibbs free energy, you can skip this part or brush up on it and come back, or just keep watching, whatever you want to do. As you may know, delta G is dependent upon enthalpy, delta H, and entropy, delta S. The delta H of dissociation is dependent on three different factors: separation of solute particles from one another, separation of solvent particles from one another, and the interaction between the solute particles and the solvent particles. The delta S increases because there is more disorder caused by the dissociation. Well, that should be about it for solubility equilibria and the solubility product constant. I hope, and I'm confident, that you have learned something worthwhile from this video. This is Professor Positron from Fancy Science University, signing off.